Let's look again at this situation where we have the water being boiled, only now let's put it in a piston cylinder arrangement where the piston is free to move. And in this case, we'll make the piston weightless at first so that we still have our 14.7 psi or atmospheric pressure inside this vessel. So as the water boils, it pushes up the piston, and again we heat the water to the point of boiling. It boils, that's the saturation temperature at 1 atmosphere or at 14.7 psi. The saturation temperature is 212. And it boils on across, as we discussed earlier, until you have a saturated vapor, and then the volume can go on up. Now let's see what happens when we add some mass to this piston. Add a little weight on this and double the pressure inside. If we double the pressure inside, by the way, if we plot this as a T versus P, we'll call this our saturation curve. T versus P, here we had P of 14.7 here and T of 212 here. That point here would represent saturation temperature and pressure. So if we add weight to this piston and raise the pressure, then we'll boil at a higher temperature. So if we make the pressure, say, 30 psi, then the boiling point at 30 psi will be about 250 degrees. So about 250 degrees will be boiling here. And then we'll have a similar sort of thing. We call these isobars. Here P equals 14.7. Here P equals 30. And you'll see that the volume doesn't get as large when it becomes a saturated vapor. And then it goes on up from here. You can continue with these isobars, adding more and more weight to this piston, putting a higher and higher pressure on this. And you'll notice that the liquid will get slightly larger, and the volume will get, and the vapor value, the volume will be slightly less large. As we continue on up into higher and higher pressures, these get closer and closer together, these liquid and vapor values, until finally you get to where there's no difference at all. That point is called the critical point. And above the critical point you cannot have a liquid. Above that critical temperature, call that TC, you cannot have a liquid. For water, the critical temperature is 705.1 degrees C. I'm sorry, degrees. 705.1 degrees Fahrenheit. That's the critical temperature. Above this critical temperature, you cannot condense a gas. So we have a gas out here, vapor out here that can be condensed, and over here we have a liquid. So that's a very important concept, the critical temperature. As we go along, you'll notice that the pressure, as you raise the pressure, the temperature at which it boils goes up and up and up. So we'll have a curve that looks something like this until we get to the critical temperature. And it can no longer be a vapor that can condense to a liquid. So on this side of the curve, if we raise the pressure at constant temperature, we have a liquid. On this side of the curve, if we lower the pressure at constant temperature, we have a gas. We can use this curve here to comment on what's, by the way, this is often called a superheated vapor out here. It's at a temperature, once you get beyond saturation, you start to add more energy, you'll heat the gas up to a higher temperature. So it's at a temperature higher than its corresponding saturation temperature. So over here we'll call this superheated. Because if another thought experiment that you can take is you can take a point here, and suppose we go in several directions with it. Suppose at constant pressure, we raise the temperature. You know that at constant pressure, if we raise the temperature above the saturation temperature, we have a superheated vapor. So if the pot's sitting on the stove, let's say, and we boil it up once it's all gone and there's only vapor in there, the temperature is going to go up and it's going to become superheated. However, the pot's sitting on the stove and you turn off the heat and you cool it down at constant pressure, then the temperature will drop. So that's sometimes called a subcooled liquid, and you'll see that word, subcooled. It's just another word for liquid, but relative to saturation at a given pressure, it would be subcooled. Another way of looking at that is to take this point, have the pot on the stove at a fixed temperature, and then raise the pressure. If you could squeeze it down and raise the pressure, then it will go definitely into the liquid phase. Now if you had and so that will be often called, because you've added pressure to go into this region, the liquid region, another word for this is compressed liquid. So compressed liquid, they both mean liquid that's not saturated, but one term says subcooled. It's just thinking of it relative to the temperature relative to the saturation temperature at a given pressure. We call it subcooled. Or if we have a higher pressure than the saturated pressure at a given temperature, we call it compressed. Two words for a liquid. And the gas we generally just refer to as superheated. However, if you had the pot sitting on the stove, and don't try this, if you had, say, a pressure cooker sitting on the stove and suddenly it broke open or no longer could hold its seal and the pressure suddenly dropped, then the boiling liquid would suddenly go toward the gas phase. And if you drop the pressure on a boiling liquid, then it will try to become a vapor because it's below its saturation pressure. So using this with a couple of thought experiments can help you solve properties problems and figure out where you are in terms of liquid, vapor, or mixture. Again, this is looking at this graph with respect to this graph. This is the liquid region over here, vapor region over here. If I'm given a property and I know the temperature, say is 14.7, and I go to, and I'm told the property is, say, 10 feet cubed per pound mass, well, I know that at 14.7 VF is 0.0167 and VG is 26.8, something like that. 26 point, let's see, let's get it right. 26.78. And I'm told that the volume of the mixture is 10, then I can look at it with respect to these 2 points and find out that it must be a mixture here. If I was told the volume was 0.0160, well, that's below 0.0167, so it must be over here in the liquid region. I would know that was a compressed liquid or a subcooled liquid. And finally, if I was told the volume of steam, water, at 14.7 psi was, oh, I don't know, 200 feet cubed per pound mass, way out here somewhere, then I would know from thinking of this graph that I'm in the superheated vapor region. So keeping these two curves in mind can certainly help you when you're trying to determine from two properties whether it's a liquid, vapor, or a mixture, and that's certainly the starting place that you want to go from. Determine what the phase is, what the phase condition is, and then go from there to find your properties.